So, hi, I just wanna flex my long hair today. So, here we have second part of our modes of heat transfer, which will be focusing on convection. So, this is just a brief discussion of what is convection all about, and of course, the basic formulas governing it, and then types of convection, and more details about it. So let's start. So first of all, I will be highlighting again our learning objectives for today. So again, we have to be familiar with the different parameters and the properties involved in heat transfer. And then we have here specifically convection. We are done with conduction, and our next video will be about radiation. And then we have here recognize the difference of conduction, convection, and radiation from each other. So the goal that we will be meeting for today is to recognize the difference between conduction and convection, since that is only the two topics that we have discussed or we will be discussing. And then lastly, we have another objective here is to understand the use of the formulas of the different modes of heat transfer. Again, our focus today is on convection. So let's proceed. Again, this is just a recall. So I will be starting by defining what heat transfer is. So heat transfer is thermal energy in transit due to a spatial temperature difference, meaning again, in heat transfer, temperature difference or temperature gradient is a mass. So when there is a temperature difference, heat transfer occurs. Now we are going to define what is convection. So convection is a mode of heat transfer in which heat is transferred due to the mixing and motion of particles of a substance. So we have here another definition. It occurs between a fluid in motion and a bounding surface when the two are at different temperatures. So I will be highlighting this next statement. The convection heat transfer mode is comprised of two mechanisms. So what are those? So in addition to energy transfer due to random molecular motion, so we have here, this is also termed as diffusion. So energy is also transferred by the bulk, or we term also this as macroscopic motion of the fluid. So the convection heat transfer is comprised of two mechanisms. One is the random molecular motion, and then the other is the bulk or macroscopic motion of the fluid. So this fluid motion that I mentioned is associated with the fact that at any instant, large number of molecules, or what we call macroscopic or bulk, are moving collectively. So this motion in the presence of a temperature gradient or a change in temperature contributes to heat transfer. So as I have also mentioned in conduction, molecular motion is very essential in heat transfer. So in general, so as a summary of this convection's definition, so in general, we have described the convection heat transfer. So convection as a mode of heat transfer is an energy transfer occurring, so it occurs within a fluid due to the combined effects of conduction and bulk fluid motion. So again, convection as a mode of heat transfer is energy transfer occurring within a fluid due to the combined effects of conduction and bulk fluid motion. So, I guess that is quite enough for you to recognize the difference between conduction and convection. So, since we have conduction as surface-to-surface interaction, and then we have in convection the fluid-surface interaction. So, as a consequence of the fluid-surface interaction in convection, there is the development of a region in the fluid through which the velocity varies from 0 at the surface to a finite value. That is why you see the infinity sign as a subscript here associated with the flow, wherein u is the velocity. So this region of fluid is known as the velocity boundary layer. So as you can see the velocity distribution there in the image, or this is also termed as hydrodynamic boundary layer. So in addition, if the surface and flow temperature differ, so we are talking about S as the surface, and then the infinite symbol here represents the fluid. So in addition, if the surface and flow temperatures differ, so if they have temperature difference, there will be a region of the fluid through which the temperature varies from the temperature of the surface at y is equal to 0. So as you can see there, y is equal to 0. And then we have Ts, or the temperature of the surface, to T infinite, wherein the infinite sign represents the temperature of the fluid. So again, if the surface and flow temperature differ, so there will be a region wherein that is a region of fluid through which the temperature varies from Ts. So that is again the temperature of the surface at y is equal to 0. So as you can see, so that is the Ts there in the image. And then we have T, or temperature of the fluid, 2 in the outer flow. So as you can see, our graph is from Ts to T infinite, or the temperature of the surface at y is equal to 0 to the temperature of the fluid. So this region is what we call the thermal boundary layer. So if we have the velocity distribution, as you can see in the image, we call it the velocity boundary layer or hydrodynamic boundary layer. In here, the temperature distribution, we call this thermal boundary layer. This may be smaller, larger, or the same as the size of the velocity, but it depends on how the velocity varies. So it may be smaller, larger, or it may be the same. We cannot say that. It depends upon the variation of the velocity. So in any case, if the temperature of the surface, which is Ts, if the temperature of the surface is greater than the temperature of the fluid, convection heat transfer will occur from the surface to the outer flow. Again, if in any case, if the temperature of the surface is greater than the temperature of the fluid, convection heat transfer will occur from the surface, of course, to the outer flow, wherein there is our fluid. So now I am introducing here two kinds of convection. Again, convection. Why am I always saying convention? Is this national convention? Sure. So next we have two types of convection, the free convection and the forced convection. So for the free convection, if you heard the term natural convection that is also the same as the free convection. So in free convection, we have here the definition. In simpler terms, the free convection, or again, the natural convection, is the substance is wherein the substance moves because of the decrease in its density, which is caused by an increase in temperature. So in here, it is highlighted the relationship of density and temperature. So in addition, the flow is induced by buoyancy forces, which are again due to density differences caused by temperature variations in the fluid. Again, in heat transfer, we are always talking about temperature variation, temperature gradient, change in temperature. And then next we have forced convection. So in here, the substance moves because of the application of a mechanical power such as that of a fan or any other mechanical power. And in here, in forced convection, it relies more on external forces. So we have here example of free convection. So in general, hot fluids have a lower density than cold fluids. So that is quite related to the term thermal expansion. And then heated fluid naturally rises and the cold fluid moves downward. So again, heated fluid naturally rises and then the cold fluid moves downward. So they create complex patterns such as convection rolls in a pot of water. So water in pot, as you can see in the image. And here in the air in the room, or hot air rising above a fire. So of course, a fire also produces heat. So there is also, as you can see, there is a pattern created there by the fluid. Generally, we cannot see those patterns, but and sometimes we feel it. Of course, we will be having also examples for forced convection. So convection can also be forced. As I mentioned earlier, we refer to forced convection as convection introduced, or this is force due to the help of mechanical power or external forces. So for example, we have here blood circulation and then engine cooled by pumped air or water, wherein in this engine cooled by pump air or water, there is a usage of pump. So in general, we speak of forced convection when the flow is caused by external means or external forces, external factors, such as by a fan, a pump, or atmospheric wind. So again, forced convection is caused by external factors, and then natural or free convection is caused by natural forces. So again, I think I mentioned convention again. So forgive me because I always say convention instead of convection. Again, this is the most important part wherein there is the formula for convection. So we have here Q is equal to H multiplied by Ts minus T infinity. So regardless of the particular nature of the convection, regardless of the particular nature of the convection heat transfer process, so regardless of the nature of the convection, the appropriate rate equation or the appropriate formula is provided here, wherein Q is the convective heat flux. Again, this is per area, so the unit is watt per square meter. And then this is proportional to the difference between the temperatures, or what we call T infinite is the fluid temperature. And then we have here Ts, the surface temperature. So again, the convective heat flux is directly proportional to the temperature difference, to be exact, the fluid temperature and the surface temperature. And then we have here H, the convection heat transfer coefficient. So this parameter, the unit of this parameter is watt per meter squared Kelvin. So again, since the convective heat flux is in watt per meter squared, so you must be using temperatures in Kelvin, since our H, or our convective heat transfer coefficient, is in watt per meter squared Kelvin. So in general, this expression or this formula is also known as Newton's law of cooling. So when Q, or our formula, the Newton's law of cooling, when Q, convective heat flux, is equal to H multiplied by Ts minus T infinite is used. So when we use the Newton's law of cooling, the convection heat flux is presumed to be positive if heat is transferred from the surface. So if Ts, or the temperature in surface, is greater than the temperature of the fluid, and then negative if heat is transferred to the surface wherein the temperature of the fluid is greater than the temperature of the surface. So, however, if the temperature of the fluid is greater than the temperature of the surface, there is nothing to preclude us from expressing Newton's law of cooling as, so here's the formula, is equal to H multiplied by the temperature of the fluid minus the temperature of the surface, since again the temperature of the fluid is greater than the temperature of the surface. So in which case, heat transfer is positive if it is to the surface. So this is just a very short discussion of convection, since I am just introducing to you modes of heat transfer. So next time that I will be producing a content about convection, I will be highlighting the most important dimensionless group in the analysis of heat convection. So that includes Nusselt number, Reynolds number. So please support me up to my next videos. So, thank you for today. If you wish to have a copy of this PowerPoint presentation, and if you also have some question, clarification, suggestion, recommendations regarding the topic, kindly email me at ryannicolo5@gmail.com. So, don't forget to subscribe. Thank you.